Yeah, hello everybody. Really excited to be here and introduce our session here this afternoon, or morning, depending on where you're at, but either way, we're all here and we're gonna be talking about air and water systems. And so I'm gonna just do very brief introductions. Each talk is gonna be about 15 minutes long, and we're gonna have 5 minutes for question and answer after that. So I'm gonna invite people to come up to the podium and ask their questions. I think that's worked out the best for the past sessions. And so with that, we'll go ahead and bring Hailey Summers up. Dr. Summers just finished her PhD degree at Colorado State University in mechanical engineering. She is going to be working as a life cycle expert in industry here in about a month or so, not before taking some well-deserved time off. So with that, I'm going to turn it over to Hailey to talk about water life cycle methodology. So Hailey, I'll hang out until everything is good to go, and then I'll jump off.
Okay. So it's interesting. When I say share screen, it gives me the entire screen. Okay. Share. And then are you seeing my presenter mode?
Yep, everything looks perfect. You sound great. So take it away.
Okay. Excellent. All right, thanks for the introduction. So as Jason mentioned, my name is Hailey Summers. I just finished my PhD at Colorado State University. Today, I'll be covering some of the methods that I put together as a part of that PhD program. And it's going to be on advancing water scarcity footprint methods, particularly for arid regions. So I worked on a project for the USDA. It's called the Sustainable Bioeconomy for Arid Regions. And the mission statement is to build a sustainable bioeconomy for arid regions to improve quality of life in rural communities and native nations. And the SBAR, Sustainable Bioeconomy for Arid Regions, in the map is down in the American Southwest, so in Arizona and New Mexico. And if we're going to be looking at the sustainability of this region, I think a really important thing we should consider is the use of water. So if we look at drought across the US, we see that the West particularly is in a state of persistent drought. But really, if we zoom in on that Arizona and New Mexico region, we see that most of the state is in a heavy state of drought. So we still grow a lot of things in this region though, right? This is a map of the county breakdown of percent land allocation towards agriculture and farms. And in the Southwest, agriculture means irrigation. It really requires a lot of supplemental irrigation. And so 90% of croplands in Arizona are irrigated, with about 74% of the total water use in Arizona going towards agricultural products. So when we think about the tools we have, though, to quantify the impact of fresh water, and we think about running our Tracy categories from the EPA in the US, we don't have water as a standard category. And so I started thinking, should we be quantifying water as a part of LCA? I think a lot of people in the community would also agree that the answer to this is yes. But then when we're quantifying water, is the quantity enough, or is all water valued equally? By the end of the presentation, I hope to convince you that the answer should be no, and that we should have metrics of valuing water use at various times in various regions. So we can think about this concept looking at irrigating different crops. So in Arizona and New Mexico, 4 primary crops are corn, wheat, alfalfa, and cotton. And this is a breakdown of the amount of water they need throughout the year. And when we look at this, if I had just asked, what's the crop with the largest water impact in the region, you might naturally think, well, what needs the most water? And I think that's the first step, is saying, how much water do the crops need? But then if I told you a follow-up data point that this is when, this red line is when water is available, then you might think, well, okay, maybe we should just best match that line. Should we go, is it timing? Is it quantity? What's the most important thing to consider? So I think in understanding the impacts of water, it's not just the amount, it's also when the water is available in the region, and that can give you a better metric to go off. So I'm not the first person to think about this. A few years back, a method was presented by the working group in Canada. They presented methods for, they were called AWARE. It's the Available Water Remaining method. And it's compliant with ISO 1446 of generating a water scarcity footprint. The idea is you need to understand the amount of water needed, and then you would weight that by characterization factors to get a water equivalence. It's very similar to greenhouse gas accounting, where you get a CO2 equivalence. In fact, the units you get out of a water scarcity footprint are cubic meters equivalent per a functional unit that involves area and time. So the biggest part of understanding a water scarcity footprint is understanding how you quantify characterization factors. That's the most important part. How do we weight the water use? And for the AWARE method, the standard that's been developed is using a method called availability minus demand. And you take the region average, in this case, the US average of the availability, water availability minus demand, and you would compare each individual county and month, county I and month J, availability minus demand, to your region average. We'll go into this a little bit further. Availability minus demand accounts for natural runoff, that's what's available, and it also then subtracts the different demands which are coming from the ecosystem and the society. So visually what's going on, I'm a visual person, so this helps me. If you think about the blue box being what's available, you have natural runoff equals your surface runoff and your subsurface runoff. This is all that we have to work with fresh water. It's what's available. You need to then subtract the ecosystem water requirements and societal water consumption, and that gives you availability minus demand. That's what's left. And so the AWARE methods take each month and county AMD and compare that to the US average to give you a weighting factor. And Argonne National Lab actually generated the set of numbers that I'll be using, and they generated AMD values for all US counties and monthly resolution. That gives you characterization factors at a monthly and county resolution across the US. So I was just gonna use this method when I started this research to answer some questions relevant to my USDA project, but I immediately ran into some limitations. So I want to talk about those limitations and then how I went around them. So the AMD method, when it was generated, the characterization factors are sort of on this exponential trend, and the organization decided they wanted to apply some cutoffs. The first cutoff happens at the minimum, so characterization factors can't go below 0.1. That's when a particular AMD, or availability minus demand, would be greater than 10 times your US average. The upper cutoff happens at when availability minus demand is less than 1% of your US average. And so the characterization factors are sort of bound by these two values. But when I started looking into it, I realized that these cutoffs led to a lot of data loss, and particularly at the upper end. So at that maximum value of 100, there's about 7.2% loss of data at the US level. So 2,662 data points are sort of truncated and held at that maximum. There were no results at the bottom, which is kind of interesting, but I really want to focus on this maximum because where this is happening is particularly important in the arid locations of the US. So these upper cutoffs, they're applied sort of as this curve reaches a point of discontinuity, so as it approaches zero, and then therefore it actually doesn't account for any values that would be negative. You would get a negative AMD if you had greater demand than available. So if you needed more water than what's available. So all of those values are truncated and set at 100. And that's exactly, by definition, an arid region when you need more water than what's available. So for me, when I was trying to answer questions for the USDA project, this was somewhat limiting. So I went back to the drawing board, and in the process of developing the AMD method, the organization actually had omitted another method, the demand to availability. So this is a ratio instead of a difference. They had deemed it not relevant for answering global questions. They actually said this is a metric for aridity. And so I said, this is great, this is exactly what I need, but it hadn't been developed beyond just this mention of the ratio. So I've taken it and I've fully developed it and I've applied it for this USDA project to show an example of how it can be used. So I developed characterization factors similar to the original AMD method by doing a ratio to a relevant region average. Then what happens is, because you're doing a ratio of ratios, your data ends up linear. And you'll have a singular maximum and a singular minimum. Those values will change depending on the region you want to assess. But the important note here is that there's no cutoff. The DTA method now accounts for those values that were lost previously, and it can account for values where you have greater demand than availability. So again, I've developed characterization factors. We're going to be zooming in on Arizona and New Mexico using the data from Argonne National Lab, the raw values of demand and availability. I've created a localized region average for Arizona and New Mexico using that data, and I weighted things by human water consumption. This is just consistent with what the original methods and approach had taken. And I've done this for a county and monthly level similar to the original method, just so we can look at differences. So what we're going to look at now is the annual average characterization factor. So I've truncated all 12 months into an annual value, and this is the original AMD method. So what's important here is to note, again, that the truncations, so those cutoffs up at the 100 value, you can see in the color bar at the bottom, there's a histogram of data. You can see that the largest bar, the largest number of occurrences happen at the 100 value. And so originally using the AMD method, you weren't able to compare counties to counties very well. There was a lot of just 100 versus 100, and that doesn't give you a lot of insight. When I ran the characterization factors using my new DTA method, we can see the full suite of data distributed here on the color bar now. The numeric values are not meant to be compared. In fact, they really shouldn't be compared because the methods are intrinsically different. So we're just looking at the map side by side to look at different trends. But what we can see in the DTA method on the right is that there's a full resolution of color. We see now that every county has a unique number and we can compare them. Particularly what we also see is that there's this Curry County, the far east, that has the largest or most red value, right? So it has the highest characterization factor. That comes from the development of the characterization factors themselves. So to get a high value, you would need a very high numerator. And to get a large value for your numerator, you need a lot of demand and very little availability. And that's exactly what's happening in Curry County. And that's okay with this method. What we see now is that full realization of just how much demand was in Curry County, whereas previously that was truncated. So now with the new DTA method, we can realize some additional insight. So comparing counties like Curry to Roosevelt, originally those were ranked the same. Now we see that Curry's about twice as high as Roosevelt. Furthermore, Curry and Sierra were originally ranked the same, and now we see that Curry is about 10 or more times as intense as Sierra County. So I extrapolated this beyond, that was just our annual characterization factors. So now we're going to go all the way out to water scarcity footprint by looking at an alfalfa case study. So I took the distribution of water needs for alfalfa and multiplied by the demand to availability characterization factors to get water scarcity footprint. We're going to look at the two methods side by side. We see kind of similar trends of the characterization factors themselves. This is just to point out the decision-making abilities within the two methods. So originally we had a lot of the values being the maximum water scarcity footprint. So this was, again, in regions like Curry and Roosevelt, we couldn't really tell the difference. And now we can zoom in and actually look at numeric quantifiable differences between water scarcity footprints in the region. So I want to take this a step further and really tie this all the way back to the USDA project that I've been working on. The USDA project is looking at bringing in outside crops that we currently don't grow in the US. In this region particularly, 2 crops, and they're known for a couple added benefits. The crop guar is known for low water use, and it's known for being drought tolerant. So it's a good candidate for this region. I've sort of bolded here this low water use. So prior to me analyzing the water scarcity footprint in this region, we really just thought about this crop as using less water. So it was a total cumulative water, and that's why we would tag this crop as low water use. But as I've shown, that's not always enough. We need to consider when water is available and the whole irrigation regime. So I've pitched a new question, which is, will guar have a lower water scarcity footprint than existing crops in Arizona and New Mexico? If we adopt this crop, will it lower the water scarcity footprint? So I've done a very similar thing to alfalfa, but now I'm including guar's irrigation schedule and 4 crops in the region. I'm using the demand to availability characterization factors, and I'm going to compare, again, the original AMD resolution to the new demand to availability to answer if guar can have the lower water scarcity footprint than these other crops. So what we're looking at, each county, we're just looking at the lowest resulting water scarcity footprint. So I ran the 5 crops. The first thing you'll notice in the legend is 2 are missing, and that's because cotton and alfalfa just never had the lowest water scarcity footprint. So growing those crops in the region will always have a higher water intensity than these 3 crops. From the original method, we see that guar has the lowest water scarcity footprint in 35 of 48 counties. But when we start to think about some of the decision-making questions, let's say hypothetically we adopt this crop a lot in this region in the future. We wanted to locate an on-site localized processing facility to process the guar plant to the products. If we did that, it'd be advantageous to locate it somewhere where you had a lot of surrounding access to low water scarcity footprint. So if you could grow the crops close to the processing facility and also lower your water needs. So you might consider that Curry and Roosevelt, in this case, would have been a good location for that processing facility. When we look at the results from the new method, though, we see actually almost a completely inverse trend. So we do see more guar. So this means that guar has a lower water scarcity footprint in more counties using this method. But we see that the 2 counties that we previously considered are no longer in the picture. And so this method increases the resolution and allows you to realize better decision making for regionally relevant questions. So just to wrap up here, the AWARE A&D method limits characterization factor resolution, particularly in arid regions, because it doesn't account for demand greater than availability. The DTA method increases this resolution in arid regions because it doesn't apply cutoffs and it encompasses the full data set, including those values, those locations where water demand is greater than availability. And looking at the guar case study, we see that the demand to availability method increases regional insight and decision-making abilities. So I think that's everything that I wanted to show today. And I think Jason, are we doing questions now and then, or the end?
Yeah, thanks for that, Hailey. So we can do the virtual clap that everybody is doing. I know I can see everybody clapping out there now. So we got a few minutes for questions. So if there's any questions, please feel free to jump up to this podium here, click on that. I'll give it 15 seconds of silence before I dive in and ask Dr. Summers a couple of quick questions. So any questions from the audience? All right, so I counted to 15 in my head. So if there are questions, please jump up to this podium. I guess, Hailey, if I might ask a quick question. So a lot of work is done, including this, geospatial resolution. One of the things I pay attention to all too much is, water flows and rivers and the desert Southwest and all these different things. So maybe comment a little bit in terms of temporal resolution. Like obviously there's a huge drought in the Western United States right now. And so I might just ask for you to comment in terms of how these methods either incorporate or don't incorporate these kind of more annual based changes that we're starting to see in terms of how water is coming down different watersheds. Does that question make sense? And can you comment?
Yeah, it makes good sense. So, and it's a great question because I actually think it's another limitation of the method right now, but that's fine, right? This method it's very recent. The first presentation of AWARE was in 2018. And the first pass, so when I mentioned that the data came from Argonne National Lab, the values I used are river flows and values that are averaged over the past 30 years. So it is sort of a static assessment right now. So the monthly availability and monthly demand values were averaged over the past 30 years. And it is a singular value. So you could, in theory, go in and if you knew those changes over time, you could make this model temporal. You could, if there's future projections of water flows, you could take it into the future. And so I think that would be another iteration of this method. We just need a little more time with it, I think, because it is so new, and we need people interested in advancing the method and using it and coming up with things like temporal resolution that can continue to increase it and continue to get this method to be more universal.
Great. Thanks so much for that, Hailey. I guess I'll wait another 5 seconds if there's any other questions. Otherwise, we're going to, here we go. Somebody's coming up.
All right. Hi.
Chris.
Great talk. Really fascinating. I wish my Hai Nguyen was here. She had to be somewhere else at the moment, but you're making me think of her work. She's a student I've been working with, and she has been using regression models to basically make regression models with daily precipitation, temperature, etc. in the future. And so I'm just wondering, and then there's also a number of people working with hydrology models, and they're running them on a daily time step and all this stuff. And I'm just wondering if you had talked to those people, and I will be asking her later, and as we review your presentation, if there's a way to think about, maybe addressing some of the temporal and also thinking about future climate with one of these sort of methods, because we're characterizing drought with different indices and stuff anyway, like SPI and that. So I was wondering, just your thoughts on the hydrology and that kind of data might be useful.
Yeah, I think it's a great question with the past. These methods, as I mentioned, are static, not very highly resolved. You look behind the scenes as far as the hydrological models, and so I think that there's a lot of room for improvement there. I think this is really a first pass of a way of valuing water, so a way of valuing it as not equal just because it's the same cumulative total amount, but adding in another layer of complexity with hydrological modeling would be very beneficial. I haven't spoke with those people that you mentioned, but yeah, I could see that to be another way to just to improve this method.
Great. So Hailey, I think that I might do the virtual applause again. So thank you so much for your presentation. Thanks, Chris, for that question. Hailey will be around throughout the session, so folks can connect with her outside of this to continue to ask questions. So with that, we'll go ahead and excuse Hailey and bring up the next speaker. So the next speaker is Austin Banks. He is a master's candidate in mechanical engineering at Colorado State University. When he's not out hiking the Colorado Trail, I recently found out he is a hardcore downhill mountain biker. So we're always learning things about people we work with all the time. So with that, Austin, I'm going to go ahead and turn it over to you to talk about water again, another water talk. And so I'll just wait until you get your screen up and sharing and make sure everything's good to go before I pop off.
Thanks for the introduction, Hailey. I always wondered why we never considered water consumption in LCA, so I think it's really cool what you've been doing. Okay, so I have a second screen being shared currently, and is the presentation showing?
Yep, it looks perfect. You sound great, so take it away.
Okay, awesome. All right, well, my name is Austin Banks, and today I'll be presenting on a water quality integrated techno-economic assessment and life cycle analysis of biofuels from filamentous algae. But before I begin, I'd like to say thanks to all my friends, collaborators, and colleagues at the Powerhouse Energy Campus at Colorado State University and Sandia National Laboratories in Livermore, California. This work would not have been possible without everyone's contributions. I will now give a brief background for the motivation of this work. It is important to understand the symptoms of mismanaged watersheds. These images are becoming more common in water bodies around the United States and the world. Human activities cause leaks of nitrogen, phosphorus from wastewater treatment facilities, urban land, and predominantly agricultural land. This nitrogen and phosphorus accumulates in our watersheds and feeds out of control algae growth, known as harmful algal blooms. Harmful algal blooms are nature's way of dealing with excessive nutrients in the water, but sadly, they can result in eutrophication, depleting the oxygen and suffocating surrounding aquatic life. Harmful algal blooms cost us millions of dollars every year from tourism, fishing, property value, and mitigation losses. And there does not appear to be a clear solution for dealing with this issue. So as the population continues to grow, is there any hope for improvement? I would argue that controlled growth of algae upstream is a viable option. Here are the two most popular methods of cultivating algae commercially. On the left is an open raceway pond, and on the right is a photobioreactor. Both of these systems allowed for engineered strains of algae to thrive under the various conditions they experience. But these systems are costly and they require constant fertilization of nutrients and carbon dioxide. And in some cases, they compete for land that would otherwise be used for agriculture. Neither of these two systems were used in the following analysis because they treat algae as a product. Algae actually provides a service for removing pollutants, especially dilute nutrients from our watersheds, as we'll see. Here are some of the pictures of the system we modeled, the attached algae system. Attached algae systems are scalable sequestration units that absorb atmospheric CO2 and pollutants like nitrogen and phosphorus. Excess nutrients that are contaminating surface waters would otherwise accumulate in wetlands, leading to eutrophication and loss of biodiversity. Instead, the water is diverted at various points along the watershed and flown over an attached algae system, creating algae as a byproduct. The water is passively filtered by the algae, which physically removes pollutants and transforms them into biomass fit for biofuels or other bioenergy products. This novel system promotes algae growth in a controlled environment and provides a service for cleaning our water and preventing harmful algal blooms downstream. I will now go over a brief overview of the basic model structure. So as we can see, there are two major model inputs. Those feed into the process models used in this system, and now from those process models, we get our outputs in the form of a techno-economic assessment and life cycle analysis. I'll explain these in more detail, beginning with water quality data. USGS released a suite of publications that estimate important water quality parameters in each of the 5 major hydrological regions in the United States. The data used in this presentation is aggregated at the state level. You can see from the heat maps that the data is available at a higher resolution, but to simplify this analysis, we aggregated at the state level. We use total nitrogen, total phosphorus, and flow data as inputs for the algae growth system. And specifically, we looked at the delivered fraction, which represents the amount of pollutants that are delivered from each state downstream to the terminal receiving waters like lakes or estuaries that feed the ocean. So after we combined the flow and the load data, we determined state level concentrations. So normally, nutrient reduction is tackled with a % reduction, but this system treats water to a specified target limit. And I know it's hard to paint a broad brush for acceptable limits because there's so much variability within each state's networks of lakes, rivers, and streams. But just for reference, the EPA typically defines an acceptable total nitrogen and total phosphorus limits as seen by the red lines. But I mean, we're still seeing harmful algal blooms almost everywhere we go. So in the future, we need to receive reductions in total nitrogen and total phosphorus so that we can reduce the propensity of harmful algal blooms. But to facilitate this analysis across all states, we tested 2 low limits in the dilute nutrient range. So as water quality standards become more stringent, we need to estimate the costs associated by achieving these limits. This may seem like an absurd target, but attached algae systems thrive when nutrients are dilute, whereas conventional wastewater treatment technology is not likely to meet these target concentrations in an economically feasible manner. Moving on, we will now discuss the other major input data used in this model, which is the weather data. So not all light promotes photosynthesis. Algae need light in the PAR range, which is from 400 nanometers to 700 nanometers, to promote active photosynthesis. Similarly, not all states have the same number of days of sunshine. New Mexico may be a desirable location for an attached algae system because of the access to sunlight, whereas Washington may be undesirable because of the number of cloudy days it experiences. Another important input we used was temperature, because the temperature of each region influences the algae growth. Algae are comfortable between a temperature range of 60 to 70 degrees Fahrenheit. Anywhere outside that range, you'll see the productivity starting to drop. So ideally, a candidate location will have a high PAR flux and temperatures within the optimal growing conditions for the algae. We incorporated light and temperature data from across the US to estimate the algae growth in each state. So we've just discussed the major model inputs, and we'll now explore the algae growth model used. So from the weather data, we approximated state average algae growth productivities in grams per meter squared per day. This allows us to size the attached algae systems to treat total nitrogen and total phosphorus loads to a specified level. This translates to the total amount of area needed for treatment by an attached algae system in each state. We also estimated the cost for producing the biomass, which is important to the economics of the entire system. So after determining how much algae is produced in each state, we then converted that biomass into biofuels. So here is a overall or basic process model of the system boundary placed around the attached algae system in the biofuel conversion process we tested. On the left, atmospheric CO2, nitrogen, phosphorus, and energy all feed the attached algae system. After harvesting and dewatering steps, the algae then goes into 2 different biofuel process models. We tested anaerobic digestion and hydrothermal liquefaction. For anaerobic digestion, it produces a gaseous biofuel, which we'll call biocompressed natural gas. Hydrothermal liquefaction, on the other hand, produces a liquid biofuel, which we'll call biodiesel. After accounting for all the material and energy balances of the system, we determine the cost of the biofuels by conducting a techno-economic assessment. The TEA is broken up into the structure and the tools, where we determine what the minimum selling price is by ensuring a net present value of 0 and an internal rate of return of 10% over the 30-year operation lifetime of these facilities. We also used Excel spreadsheets and Aspen Plus to aid in these calculations. Not only did we consider the economic feasibility, but we also considered its environmental impacts through a life cycle analysis. So the structure of the LCA accounts for all the cradle-to-grave impacts of this proposed system. This translates to a well-to-wheel system boundary for a biofuel system. So we considered all the steps from resource acquisition, design and manufacturing, distribution, product use, and recycling and disposal, and completing that loop. We used OpenLCA and EcoInvent databases to obtain the life cycle inventory data in order to get back out what these environmental impacts. And in particular, we looked at global warming potential and eutrophication. We'll now dive into the results for the techno-economic assessment and life cycle analysis. For the sake of time, we will only be presenting the hydrothermal liquefaction biofuel selling prices. The anaerobic digestion costs follow the same trends as hydrothermal liquefaction, but anaerobic digestion is about 5 times the cost of hydrothermal liquefaction across all states. So now if you direct your attention to the bar on the right-hand side, you'll see that the minimum fuel selling price ranged from $7 a gallon of gasoline equivalent to $108 a gallon of gasoline equivalent, where each state's color reflects the cost of producing the biodiesel. Zeroing in on the non-applicable states, we'll see that there are entire regions where this system is not possible, specifically Montana to Wisconsin and Vermont to Maine. These states have concentrations above the specified limit, meaning reduction in the nutrients in the water is possible. But the regional weather data, specifically low temperatures, were outside the optimal growing conditions, meaning algae growth is not possible. Moving our way up the scale, we see that New Mexico yielded the highest selling price. Even though New Mexico exhibited one of the highest algae growth rates, the amount of water flowing through it is small. This small flow rate resulted in a system whose size did not hit the economies of scale we would like to see for the price to reduce. Now moving to the top of the scales, we see our top 4 candidate locations: Michigan, Florida, Texas, and California. These states are capable of producing biodiesel around $7 a gallon. And these states all had temperature and light inputs that resulted in lower biodiesel prices than the rest of the states, though the surrounding states in the Midwest are not too far off this mark. If you remember, we tested the dilute nutrient range, but across the board, these results are promising. So regardless of the reduction that we're seeing in the nutrient concentration profile, we're getting a relatively inexpensive biofuel. We'll now go over the key LCA findings. Again, for the sake of time, we'll now only be discussing the anaerobic digestion system. For this water quality integrated biofuel system, climate change and eutrophication are the most important indicators to consider. If you remember, the anaerobic digestion system produces biocompressed natural gas, so we need to compare ourselves to the alternative, fossil natural gas. On the left-hand side is the global warming potential of both the attached algae system coupled with anaerobic digestion relative to fossil natural gas. To be considered a biofuel for use in the United States, the renewable fuel standard requires a 60% reduction in life cycle emissions. We can see that this system exceeds this target, meaning the attached algae system coupled with anaerobic digestion is indeed sustainable in terms of its greenhouse gas emissions. Now looking at the plot on the right, we can see the eutrophication potential of an attached algae system coupled with anaerobic digestion relative to fossil natural gas. These results show that by switching our consumption of fossil natural gas to natural gas from an attached algae system coupled with anaerobic digestion, we can reverse the eutrophication potential. This means that an attached algae system coupled with anaerobic digestion can be utilized to reduce harmful algal blooms and clean up our watersheds. So not only can we reverse eutrophication with the system, but we also get biodiesel for around $7 a gallon. While these results are promising, optimization could yield lower biofuel prices and greater reductions in life cycle impacts. And before we finish up, I would also like to discuss the future direction of this work. So we have just seen the results for the state level model, but I would like to add to this analysis. In particular, I'm interested in looking at the total nitrogen, total phosphorus removal costs for treating the same water with a wastewater treatment facility or lagoons, or even best management practices relative to the attached algae system. We'd also like to improve the algae growth model. Specifically, the model currently takes in the ambient temperature as the temperature of the algae growth system. In the future, we think it might be wise to spend some time integrating a heat transfer model that accounts for all modes of heat transfer with inputs of the ambient conditions to predict what that temperature of the water is. So this is important because in arid regions where the temperatures can reach above 100 degrees Fahrenheit, we'll never see the water reach that level. So we need to have a little more resolution in terms of the heat transfer capabilities of the system. We'd also like to incorporate a higher resolution data to the system. So we wanted to conduct the same analysis as the state level model, but if you remember from the USGS publications, they offer data at a higher resolution. So we want to be able to pinpoint where exactly does this model make sense. And there might even be regions that were not applicable where this technology could make sense. And there might even be areas in New Mexico where an attached algae system would make sense. Lastly, we are interested in incorporating water quality trading scenarios. So this would look like receiving a subsidy for reducing total nitrogen and total phosphorus loads. Incorporating these subsidies could reduce the biofuel selling price to make this system competitive with fossil fuels. If there's anyone in the audience that is experts in any of these areas, I would appreciate you reaching out after this presentation. Thank you for your time, and I hope you enjoyed the presentation.
Yeah, so thanks very much. Virtual clapping. Thanks very much for that there, Austin. So again, questions from the audience. So feel free to jump up and join the podium here. You can just click over there and jump up and ask a question. So I'll give it the 15 seconds of silence to see if there's any questions for Austin out there.
Hey, Austin, can I ask a question?
Dr. Summers, please.
Okay, so I'm just thinking about maybe like a way you could lower the costs, right? Because it seems like you have some wiggle room with the environmental impact, right? Like GWP was pretty low and the nitrogen was pretty low. So I'm thinking like, did you just run one set of target nutrient reduction? So like that what singular value? Because I'm wondering if you can change that value, give up some leeway on how much nitrogen and phosphorus the algae would actually remove. So if you slid that line back up just a little bit, didn't be stringent, do you think that would add any value in reducing cost?
So we also tested two other limits about an order of magnitude in the opposite direction. So that cutoff resulted in about 10 to 15 states that were below that limit. So that just reduced our ability to make any assumptions about those. So we tested a low limit, which is pretty promising because if we're able to capture these nutrients at the low end of the spectrum, it'll make even more sense to capture them at the high end of the spectrum. So like we were saying, as water quality standards become more stringent, we need to make our water, make the nutrients in our water more dilute, and we need to treat them to these dilute concentrations. So I would say that these results are promising for both ends of the spectrum.
Okay, cool, thanks.
Any other questions from the audience? So I guess, Austin, I might throw one at you. I think that your model pulls together a lot of different components. And so this is kind of, sparked my interest in terms of understanding what's the largest uncertainty out of all of the points that you're pulling in, right? Because everything's pretty static, right? Growth model is static, nutrient release is static. What's the largest, if you had a magic wand, you'd be like, oh, I know this perfectly. What would you be going after?
I'd be going after understanding what the actual nutrient profiles are throughout the year so we can get a more seasonally resolved model. So currently it's a yearly averaged model aggregated at the state level. So if we can get higher resolution and seasonal variability to capture, then we can definitely isolate locations where this does make sense. whereas this analysis is a little more static in nature. So definitely some room for improvement.
Any good research project, right, has more questions at the end, or any good presentation, more questions at the end than what we started with, right? So awesome. I'll just pause for 1 more second. Well, 5 more seconds if there's any other questions from the audience for Austin. All right, I'm hearing none, so we'll go ahead and do the virtual applause thing for you again, Austin. Want to thank you very much for your presentation, your work there, and again, just reminding everybody that feel free to connect with people outside of the actual sessions that we have here. So Lynn, I think you're going to bring up Kaixin, is that right? There we go.
Yeah, okay. I just quit it. I don't know what's happening. All right.
So I'll do a quick introduction while you kind of attempt to share your screen, and we'll get started while we work on the backside with Justin to get all the technical things figured out. So your screen's coming up, so I'll do a quick introduction here. So currently Kaixin is a PhD candidate at Northeastern University. She is planning to defend her dissertation this December, and so excited to hear what you have to say. I will turn it over to you. Everything looks good. We can hear you, so take it away.
Okay. All right. Hello, everyone. I'm Kaixin. I'm currently a PhD student from Northeastern University based in Boston. And today I'm going to talk about my research, which is estimating the future industrial emissions of hazardous air pollutants in the US using the National Energy Modeling System. It's a pretty long title. So the first question is, what is a hazardous air pollutant, HAPS? People are more familiar with the criteria air pollutants, CAPS, but what is CAPS? HAPS is also known as the air toxics, which has severe adverse health impacts and environmental impacts. Well, unlike the criteria air pollutants, which mostly come from the combustion, the major source of the hazardous air pollutants are mainly from the industrial facilities and also some area sources such as dry cleaner or auto repairing store, or the transportation sectors, which including the on-road section and non-road section. So for example, benzene has been found in the gasoline, and formaldehyde comes from lots of industrial process. So the health impacts from the air toxics includes cancer risk and some non-cancer risk, such as kidney liver damage and developmental problem in children, nervous system damage, and so on. So to prevent these impacts from the air toxics, EPA has regulated the emissions of air toxics through the NEMS, National Emission Standards for Hazardous Air Pollutants. So even though the industrial facilities are the major source, air toxics are still existing in our daily life, which we should really be careful about. So recently, there are a couple of news which are related to the air toxics that have been found in the products we use every single day. Like the benzene has been found in some hand sanitizers and sunscreens, and formaldehyde has been found in the hair products. So considering the adverse impacts, there are lots of research focusing on the hazardous air pollutants. Just like the criteria air pollutants, that the streamline models from the emission to the air quality and then to the health impacts are well structured. For those 4 main steps, they can either be done separately or combining in one tool. For example, for the criteria air pollutants, researchers will use the National Emission Inventory data and then coupled with some air quality models, such as CMAQ or WorthCam model, to estimate the air quality, and then finally combine with some health benefits tool, like the BIMMAP, to estimate the health impacts. There are also some tool like EMAP, which combining all the steps together. So similarly for the hazardous air pollutants, there is a tool developed by EPA named NADA, have included these 4 steps as well. The streamline models I mentioned about works well when analyze current emission inventory or emission field, but the situation is different for the projection side. So for the criteria air pollutants, there are all kinds of models that have already embedded the criteria pollutants to do the projections under the different scenarios. This projections after some post-treatment can be the input for those streamline models to provide the future insights on the air quality. But this link is broken for the hazardous air pollutants. Currently, to our base of knowledge, there's no such models which can provide the comprehensive HAPS projections under the different scenarios. But there are some potential solutions for this research gap. One of them is taking the advantage of the technology-rich model to harness the HAPS pollutants to the already existing model. There are lots of famous technology-rich model, such as DCAM image times. Those models have been widely used as an official model for countries to provide the energy and emission projections. So for the emission projection side, the usually will be the PM 2.5 or carbon emissions. Because this large-scale technology-rich model have included the detailed level of technology, economic information, and sectorial information. And it is always used for the scenario analysis. We think it is a good resource to connect the hazardous air pollutants emissions and provide the HAPS projections under the different scenarios. So in this study, we have developed a method to link the HAPS emissions and technology-rich model. So the overall methodology is shown in the diagram. NEMS model is the energy model we used in this work. The left-hand side is the components in the NEMS model. A little bit brief introduction for the NEMS. It is a partial equilibrium model, which included the energy supply side and the energy demand side. And then the model will keep iterating until the energy supply and energy demand achieve the equilibriums. There are in total 13 modules. We are only focusing 2 of them, the microeconomic activity module and industrial demand module. So we basically couple the NEMS model with the US EIO model to calculate the HAPS emissions. So US EIO model is an economic-based life cycle assessment model. It is developed by the US EPA to assess the environmental impacts based on monetary flow. So there is a satellite table included in the US EIO, which it has compiled and calculated the emission intensities in monetary flow for all the HAPS emissions. So what we do is we basically extracted the emission intensities from the US EIO model and then map it with the NEMS industrial sectors. And then finally, we can estimate the HAPS emissions in the future. We have also made extension Python Jupyter notebooks. You can just input the results from the NEMS directly, and then you can specify the possible emission intensity improving rate, and then calculate the emission automatically. So here are some results. This is HAPS emission results at the national level, in which the gray bar represents emissions in 2015, while the different color represents emissions in 2050 under the different AEO scenarios. There are total over 200 pollutants emissions are calculated. These are only top 30 of them. From the figure, we can see except the VOC's emissions, the ammonia has the highest emissions, following with methanol, hydrogen chloride. And most of the emissions are increasing by time. The emission in high oil price scenarios and high economic growth scenarios will be higher than the rest of the other scenarios. That is because that the high oil price will shift the consumption from the oil to the natural gas, which may lead to more industrial output from the metal or machinery industrial sectors to build up some natural gas well and processing plants. Those industrial output increasing will definitely increase the emissions in the future. So similarly for the high economic growth scenarios, which will result in the industrial output increasing basically for all the sectors, and then finally have the higher emissions compared to other scenarios. So taking the advantage of the USEIO, which has the emission intensities for each sectors, we can do the breakdown analysis for every pollutant. So here's the example for the formaldehyde emissions. We have like top 5 contributors for the base year 2015 and the different scenarios in 2050. So for all the scenarios, oil and gas extraction are still the largest contributors, while other non-metallic mineral product substitutes, either the organic chemicals or petroleum refinery sectors, become a new top 5 contributors in 2050. Well, since NEMS model run it at 9 different regional level, except the national results, we can also get the regional distribution of emissions for each pollutants. Again, this is an example for the formaldehyde. The regional contribution under the reference case are showing in the stack area plot. So regional 7, which is the west-south central area, contributes the largest proportion for the national formaldehyde emissions, while the region 1, which is New England area, has the lowest emissions. Since we've already noticed in the last figure that formaldehyde largely comes from the oil and gas extraction sectors, these trends are highly correlated with the industrial output of the oil and gas extraction from the NEMS model. So combining with the NEMS regional detail and the USEIL sector information, we can also study the industrial contribution for the formaldehyde emissions at the regional level. Again, this kind of figure can generate for any emissions included in this study. So from this figure, the formaldehyde emissions are for sure increasing by time, which kind of echo what we have in the previous slides. At 2015, the contribution is mostly gas extraction industrial in the West, while the pulp and paper industry and wood products industry are the largest contribution in the East. But in the 2050, we have seen that the paper industrial contribution has decreased, while the contribution from the gas extraction become more important. So using the tool I mentioned in the introduction, NADA, which is a tool developed by the US EPA, it has been used to inform the health risk from the air toxics, including the cancer risk and non-cancer indicators. We have also estimated the cancer risk by multiplying a scalar of the HAPS emission projection. The cancer risks keep increasing all the time, with the upper boundary of the high oil price scenarios. The final cancer risk results from the HAPS emission from the industrial source can be higher than 2,100 cases in 2050. So a couple of key takeaways here. Firstly, the technology and the sector specific emissions data from LCI database and EIO tables are integrated into an energy system optimization model in the study. So this method, secondly, this method enables the projections of all industrial HAPS emissions along with established national scenarios. It is the first such study to our knowledge. Thirdly, future emissions can be used subsequently for the air quality modeling and assessment of the potential health impacts and the social damages. Lastly, the evolution of the industrial process and pollution control efficacy is a large source of the uncertainties in our study. So lastly, this project is funded by US EPA Search Center, and it's supervised by Dr. Matt Coleman from Northeastern University. That's pretty much I want to share today. Thank you.
All right, again, virtual clapping. Thank you, thank you, thank you. Yeah, so we'll open it up to the audience for any questions from the audience. I'll do the 15-second silent time again.
Hello, thank you for the great presentation. I had a question about how the sort of national inventory might be used to set health-related risk-based limits to these types of pollutants. Here in Oregon, in 2016, we passed a program called Cleaner Air Oregon, which instead of using the federal thresholds for releases of these HAPs, takes a more stringent look at, what are the health outcomes of emitting these air toxics. So just curious if you've thought at all about like what the potential policy implications of having this national inventory are, and whether they could be used at the state resolution to help inform more stringent thresholds on emissions.
Yeah, I think there are a couple of policy implications from this study. The first thing is this NEMS model can provide the regional level results. So it cannot provide the state level, but it's still it's higher resolution compared to the national level. So it can give you more accurate projections for the future HAPS emissions. And then secondly, if we use these methods, we can get the sectoral contribution for all kinds of HAPS emissions. So when we are trying to propose a policy for the HAPS emission limits, that will be more helpful if we know formaldehyde is more come from the oil and gas extraction sector. So we will put the more stringent emission limits on the sectors, and then we can put like loose emission limits for other sectors. Not sure whether I answered your question, but
no, that's great. That was helpful. Thanks. And just a quick follow-up. You had the sort of spatial regions, and I didn't follow what are those regions based on? Is that like the EPA's regions or something else?
Yeah, that's the EPA regions. You can check online. There are in total 9 different regions. Yeah.
Okay, thank you.
No problem.
Great, thank you, Peter. Any other questions from anybody in the audience? Kaixin, I guess I might ask one question. I'm going to show my ignorance here fast, so please correct me. One of the things I'm interested in better understanding, and maybe asking you to comment on, is with criteria pollutants, for example, the location of the pollutant is important. And so I do some work in electrified transportation, so moving pollutants from the tailpipe to the actual energy production system that's located outside the city center, for example, has major health impacts. Is that true as well in terms of some of these hazardous pollutants, and are there thoughts on how that might be quantified or looked into in terms of the actual location of the emission? And if I'm totally off base, please say you're off base, and that's ridiculous, Jason. So I don't know if you want to comment.
No, I think that's a great comment. Yeah, I think there's a lot of the feed and transport of the hazardous air pollutants are still important, especially in terms of when you want to evaluate the health impacts for those HAPS emissions. So I believe there are lots of research are focusing on the feed and transport of these air toxics. I'm sorry, what's your question again?
Yeah, just whether there should be different factors applied to where it's being located, where the emission's actually being emitted, right? Whether it's in a city center or whether it's whether employees are exposed to it and stuff like that. Just kind of more of a comment or a direction potentially that the research.
Yeah, location is still very important for the HAPS emissions. As I mentioned in the introduction plans, basically they are work at the same as the criteria pollutants. You have to have the emissions, and then you have air quality, and then you have to evaluate the exposure of the air toxics, and then you will finally get the health impacts. So yeah, that's pretty important, as just like the HAPS pollutants.
Great. Well, I think we're out of time, so we'll do the virtual clapping again. So thank you so much for your presentation, and being flexible, stepping in from cleanup hitter into the third position. Really grateful for all of the engagement, the discussions, and I hope everybody continues to tune in for the rest of the conference. We're going late into the night for some people. So again, thanks everybody for the discussion. I look forward to connecting with people during the networking session and seeing the other talks. Thanks, everybody.